Okay, so hi everyone. For those that do not know me, my name is Ashley. I am a PhD student at the Institute for Astronomy at the University of Hawaii. I feel incredibly grateful that I'll be here talking on behalf of a very large, amazing group of scientists. So I wanted to start by showing the state of the exoplanet field prior to the Kepler mission. This is showing planet size and Earth radii on the y-axis and the planet's orbital period on the x-axis. Markers are colored by their detection technique. And I've also added some relatable planets for reference. So the radial velocity, or RV technique, measures the Doppler effect, or the wobble of stars due to stars and planets orbiting about a common center of mass. So RV detections are shown in blue, and you can see that they probe a nice range in parameter space. And in fact, RV instruments, including Keck, were the first ones in the exoplanet game and therefore have a leg up on other techniques, and some with baselines that are extending several decades. Now, I intentionally added the solar system planets because you can see that not only are we not really sensitive to these planets yet, but these planets are very different from what we knew, or what we thought we knew. And additionally, then Kepler came along and painted an even more complicated picture, totally revolutionizing and challenging our understanding of planetary science, including our place in the universe. So Kepler results suggested that the most common type of planets are between the sizes of Earth and Neptune, which was another planet type for which our very own solar system lacked an analog for. So despite this revelation, however, the sheer faintness of Kepler targets made it incredibly challenging to follow up and characterize the masses, the compositions, and the orbital properties of these planets. But if we take a look at the population from another perspective, and now I'm showing here instead on the x-axis the distance from us in parsecs, now we have TESS. So TESS is a fairly new exoplanet mission, which is basically surveying the entire sky and looking for transiting planets in the nearby solar neighborhood. Therefore, these planets are much more amenable to RV characterization, and we can learn more about these new planet classes and also help break degeneracies that exist in these planet parameter spaces. So fortunately, we can take what we learned from Kepler as well as other techniques and use this on the new candidates found by TESS. And this is exactly what the TESS Keck survey wants to do, is doing. Implied in the name, the TESS Keck survey is a survey that is following TESS planet candidates using Keck to precisely characterize the masses and orbital properties of these planets. TKS comprises many partner Keck institutions, including a number of UC schools, as well as Caltech, Kansas, and even something a little more local here in Hawaii. Well, I guess local for me, not for you. TKS was selected as a NASA Keck Key Strategic Mission Support Program, and I definitely practice that. This extends over multiple semesters, so there were several proposals submitted from these various institutions, and then the time of which was then pooled together so we could have optimal phase coverage for TKS targets. So with the pooled time, and this included a large number of nights over multiple semesters, as well as a very large group of scientists and therefore diverse science interests, we wanted to make sure that we were selecting the best target sample that would enable these broad science goals that we were originally applying for. And then thinking back to the population plots I showed earlier, or rather, I guess, folding in the fact that TESS has already found more than 4,000 planet candidates, how do we decide what targets we go? So how can we go from thousands of candidates to just around 100 planets? While this was not an insignificant amount of time, we didn't take this lightly. And so we decided to dedicate and write an entire paper that discussed this all in great detail. So here I'm showing the paper that discusses the TESS Keck survey science goals and target selection. This was submitted a few months ago and is also available in the archive. Very briefly, the paper lays out and details the procedure that TKS follows anytime we decide if we want to follow up a new planet candidate before extensively following it up. Additionally, we discussed this and implemented a unique target selection algorithm which ultimately optimized the final sample. And just for a little bit of historical context, the bulk of this work was motivated by the ability to reproduce these RV survey selection functions. I think this might have been apparent in the beginning when I showed the planet population by detection technique. Each technique has its strengths and weaknesses, and an important part of correcting these observed populations so we can learn some demographics and some population level stuff is being able to correct for these survey biases. And in particular for RV surveys, it's been incredibly difficult. So often we might drop a target that has a known stellar companion or a rapid rotation high V sin I. This really has been challenging to reproduce in later studies. So we implemented this algorithm. What does the sample look like? So here I'm showing the histograms for the subset population of planet candidates that can be observed from Keck. At the time of the sample construction, I think there were about 2,200 TOIs available. And of those 2,000 candidates, only about 800 of them had somewhat promising statuses. So that sample of 800 stars is shown in gray. The black sample is targets for which we acquired at least one high-res observation, and then it passed all of our successive vetting steps. So therefore, during the target selection process, these targets were available for target selection. And then finally, the orange sample is the final selected TKS sample. And a couple of things to highlight. The first thing I'd like to discuss is in the upper left-hand panel is showing the distribution of Vmag, the visual magnitude. Almost all of the brighter targets that were available for selection, again in black, were almost always selected, which was an inherent data product set by the algorithm in that brighter stars are cheaper and therefore typically more highly ranked. So this was kind of a nice sanity check. In addition, a majority of the TKS hosts are inactive solar type stars. This is shown in effective temperatures in the top middle panel, in V sin I or projected rotational velocities in the top right panel, and then stellar size shown in the bottom left panel. And then for reasons that I discussed earlier, a majority of the planets are small, and we made sure that they orbit a wide range of incident fluxes or stellar environments. And in fact, if we break this, the TKS sample down into its four major components, we have bulk compositions of small planets, dynamical configurations and system architectures, vetting for prime targets for JWST and exoplanet atmospheric characterization, and then planets orbiting more evolved stars. In fact, earlier today, Judah provided just a small glimpse into the breadth of TKS sciences and discussed the Distant Giant program, which is just one of a handful of sub-science themes for just one of those sections. So lots of awesome science coming out of TKS. So here the left-hand panel is showing an HR diagram, and then the right is showing the planet size on the y-axis and its orbital period on the x-axis. Concentric rings represent targets that were selected by multiple science cases, so the sharing or cooperation of targets, so we can get more targets. And in fact, if we look at the selected planet population from another perspective, I'm thinking something even more basic like a Venn diagram, you can very quickly see that the enormous amount of overlap, or that there was this enormous amount of overlap amongst TKS science cases. So this was kind of, as I said before, we implemented this algorithm to strategically select this sample, and this was kind of a beautiful demonstration or proof of concept of the algorithm, and was really kind of the first of its kind. So the software is publicly available and is currently set to reproduce the entire TKS sample, but we hope that it can be adapted for other surveys in the future. And in fact, I would absolutely love to get community feedback and build this into something that is more accessible to the broader astronomy community. Now, to highlight some of our early survey results. So if you tuned in yesterday, you might have heard a talk by a fellow IFA grad, Casey Brinkman. Now, Casey modestly discussed TOI 561, which hosts a sub-day period planet, and is chemically and kinematically consistent with the galactic thick disk as a metal Porbat alpha enhanced star, and that's shown in the left plot. So Casey and the rest of the TKS team obtained contemporaneous RVs with Maroon X at the same time, which locked in a really precise super Earth density with a mere fractional density uncertainty of 7%. It's crazy. And I think she said it is the most precise density for which we have so far of a super Earth planet. And the system was so fascinating that it received an enormous amount of press coverage, which included articles on CNN, Science, and Fox News, as well as a couple other places, as it's one of the oldest rocky planets discovered to date. To summarize a couple of other TKS publications, I'm actually going to use a figure from the TKS target selection paper I just discussed. So the plot is showing the stellar obliquity versus host star age for confirmed planetary systems. Discussed earlier today, the obliquity is the angle between the rotation axis of the star with respect to the orbital plane of the planets. So therefore, imprinted in this observation, there's a rich history of, or rich information of the history of the system, providing clues into potential formation pathways or past dynamical histories. So while distinguishing between these theories could be quite challenging, luckily a lot of the different underlying mechanisms operate on very different timescales. So by targeting planets with well-measured ages, TKS hopes to constrain and distinguish between some of these theories. And in fact, our TKS-3 and TKS-4 series did just that. And on that note, I'd like to highlight another single system publication that provides some population level insights. And we're actually now at the 10th, well, actually we're beyond that, but this is discussing the 10th in the TKS series. So TOI 1444b is another sub-day period planet, and I'm showing the high-res RV time series for on the left. So we tried to do a single planet fit, but it was strongly disfavored and preferred a fit that included an additional planet at 16 days, and this is shown on the right. So now this nicely ties back to the first system I talked about, TOI 561, which also had an ultra-short period super-Earth planet. Now, both of these systems have something in common, and that's that it seems to be at least one, if not more, planets. Whereas its distant cousin, the hot sub-Neptunes, which also reside on sub-day orbital periods, tend to come solo. And this was a bit surprising because it seems to share a more common history with hot Jupiters than it does from a planet that's more similar in size. And this may elucidate some very different formation and or migration pathway. And now to close out the talk, I'd like to bring it back to something a little bit more personal, which has been the bulk of my PhD thesis that focuses on test planets orbiting subgiant stars. Well, first of all, why subgiants? So by comparison, the subgiant branch is a rapid phase in stellar evolution, and the location on an HR diagram uniquely provides a precise mass and age. And this is especially true in the Gaia era. So planets orbiting main sequence or solar-like stars have been heavily studied. And then we heard a great talk by Sam Grumblatt yesterday, who performed a search for planets orbiting red giants, but what's going on in between? What is the fate of planets orbiting stars as they depart the main sequence? And in particular, the dynamical timescales for processes like circularization and inward migration are all strongly dependent on the scaled semi-major axis, which is just the ratio of the orbital distance to the stellar size. And in particular, this quantity is most rapidly changing for subgiants, which of course then has interesting implications for the fates of these planets. So here I'm showing the roughly 20 or so targets that I've been following up with Keck in an HR diagram on the left, and then a planet-size incident flux space on the right. Markers are colored by their mass significance. So essentially, the darker the marker, the more significant the detection. And as you can see with these orange-colored markers, we also have additional non-transiting planets that have been found through this survey. So we're currently working out the ensemble properties of the population, but I'd like to just highlight one. I think I'm way over time, but I'm just going to go through this really quick. You can see that the star is quite massive, and it's young. It's actually metal rich, so it's even more massive than it lets off. I think it's about 1.7 solar masses. The planet itself is also fairly massive. In fact, there's a paucity of planets that are greater than two Jupiter masses around more evolved stars, and there are a couple theories for why this is so. First is that more massive stars have more massive disks. They dissipate quickly and therefore halting this inward migration. And another theory suggests that these planets are just engulfed early on. And I'm just going to forward. So yeah, we have a ton of RVs, beautiful RV time series for a lot of these planets. They come in a wide range of sizes and masses. And I'll just leave and conclude by leaving these numbers up for TKS and then take any questions. Sorry for going over.
All right, do we have any questions in the room? Oh, we have one over there.
I'm sorry, that was hard to hear. Did you say the hot Neptune desert?
Wow, that was impressive that you could hear that. Yes, so you had one planet in the hot Neptune desert, it looked like, that had a pretty low, or didn't have a super strong mass constraint. And I was wondering if you could say a little bit about that particular system. Yeah, this one at 10,000 incident flux, or yeah, 10,000 times the flux on Earth.
Yeah, so this one, yeah, as you said, it's not quite significant yet. The 1 sigma mass here just means that there is something or some signal that happens to be phasing up with the period and ephemeris from TESS. I can't recall off the top of my head the actual characteristics of that and the host star, but we can talk offline about what this system is in particular.
All right, any other questions in the room? Anything online? No. Okay, well, if there are no more questions, one more big round of applause.